Hello and welcome to WWDC. My name is Zheng Naiwei from Apple's AV Foundation team. In this session, we are going to talk about how to improve streaming delivery reliability with new features we added to HLS Content Steering. We will cover 3 topics today. If you haven't heard of content steering, don't worry. It's a piece of HLS technology that can dynamically steer streaming traffics to improve streaming service quality. I will give you a short review to help you get on track. Then I will present the new pathway cloning feature, which can bring dynamic steering ability beyond limits to further improve the reliability of your streaming service. Finally, I will use concrete examples to guide you through how to influence server-side logics for steering traffics. Let's wait no more and get started. Back in the time, we don't have content steering. Variant selection in case of error fallback wasn't standardized in the HLS specification. And different client implementations can behave differently in choosing the next fallback variant. But a typical way to do this is to follow the variant ordering in the multivariant playlist. If a steering provider wants to specify a set of fallback CDNs, they need to list every variant from every CDNs and properly order them in the multivariant playlist. This way, in case the client player encountered a failure in the first variant, it can move on to the next variant in the playlist with the failed variant penalized from selection. In this case, we see that the client player had trouble with the 6 Mbps variant from CDN1 and thus moved on to the next 3 Mbps variant from CDN1, following the order in the multivariant playlist. If unfortunately the 3 Mbps variant from CDN1 also failed, the client player will be left with no variants from CDN1 and move on to the 6 Mbps variant from CDN2. It can do this on and on until no variant to fall back to. However, even though the playlist authoring server can control the ordering of the fallback variants, such control only happens at the point of client requesting the multivariant playlist. And once the playlist was handed out, there's no way to change the fallback ordering. This is where content steering comes into the picture. With content steering, the streaming provider can now group variants into pathways with different CDN hosts. The error fallback behavior is now standardized for content steering. Pathways are ordered by preference. In this example, the CDN1 pathway at the top is most preferred, following CDN2 and CDN3. The streaming provider also hosts a steering server, generating steering manifest for each client player. A steering manifest defines rules of pathway priorities, so the player can follow the rules in selecting a fallback between variant streams. Let's say, for example, the streaming provider is trying to offload some of the traffic from CDN1 to CDN2. It will generate a steering manifest with the new pathway priority rules. And when a client player playing from CDN1 requests for a steering manifest update, the steering server can send the prepared steering manifest with the rule changes to the client. The client will parse and see the new pathway priority rules and apply it to its playback session. In this case, the rule change switched preference order between pathway CDN1 and CDN2, so that the client player will switch and play from CDN2 immediately. Then, in case of failures, the client will first exhaust fallback variants within the current pathway, and fall back to the most preferred pathway according to its current pathway priority. In this case, if all variants from CDN2 were errored out, the client player can start to choose from variants from CDN1, which is the next preferred pathway. When we apply content steering to the global scale, it can solve bigger regional load balancing problems. Let's say our streaming service provider operates all around the world with 2 main CDN providers. To assign these CDNs to client players globally, the steering server prepared 2 different steering manifests. One prefers CDN1, and the other prefers CDN2. Then it distributes this steering manifest based on client player's region, so that the North and South America utilize CDN1 and the rest of the world utilize CDN2. At the top of the world map, we show a horizontal stacked bar representing the distribution of traffics between CDN1 and CDN2. As of right now, both CDNs are serving half of the worldwide traffics. However, over time, the streaming service provider observed a significant increase of traffic towards CDN2 because of global daylight shift. At the same time, the traffic towards CDN1 is decreasing. So the streaming provider decided to steer the Europe region to use CDN1. It does so by preparing a steering manifest that prefers CDN1 and send it to clients from Europe region. Now those client players in that region will steer traffic to CDN1, offloading from CDN2, and the global traffics become more balanced. Now let's take a look at an HLS multivariant playlist with content steering support. First, we see the EXTX content steering tag that indicates this multivariant playlist uses content steering. Then, we have a server URI attribute specifying where the client should request steering manifest updates from. Then the next pathway ID attribute specifies the initial pathway to choose for playback at startup. Then we can see that each variant stream were given an add pathway ID attribute to group them into pathways. Each pathway should have the same set of variant streams, with only difference being their URIs and media group names. In this example, we have two pathways, namely CDN1 and CDN2. Both contains two variant streams, one 6 Mbps high-resolution video and one 3 Mbps lower-resolution video, with the only difference being the URI hostname. There are also two distinct audio groups for each pathway, where they have different URIO hostnames. Here is an example steering manifest, which is a JSON document. The pathway priority field is a list of pathway IDs in the preference order. So in this case, the receiving client player would prefer CDN1 over CDN2. This is the steering manifest the steering server will provide to the European clients to let them prefer CDN1. By altering the pathway priority field in a steering manifest, a steering server can control the steering policy for every client. That's it for a quick overview of content steering. If you want a more in-depth explanation, feel free to check out my WWDC21 talk, Improve Global Streaming Availability with HLS Content Steering. However, our journey for supporting a more scalable and more reliable streaming service doesn't stop here. Nowadays, companies can access more versatile cloud infrastructures and tools to achieve things unimaginable in the past, and we have to catch up in the leap in technology. Let's say our streaming service provider has grown larger this year, and they are experimenting a new way to satisfy the dynamic traffic demands of its growing user base. They are doing it by dynamically spawning fleets of CDN servers in real time to alleviate temporal traffic stresses. For example, it can spawn a new fleet of CDN3 and want to advertise it to existing clients. However, the challenge here is that the dynamically spawned CDN info is not included in the multivariant playlist when existing clients requested it, because it just didn't exist. So what can we do to tell our client players the emergence of a new CDN? This is where our new pathway cloning feature comes in handy. It's a new feature with backward compatibility with Content Steering 1.2 introduced in WWDC22. With pathway cloning, the steering server can announce new CDNs to existing clients using a compact manifest definition. By assuming pathways are structure identical, new pathways can be created by copying and modifying existing pathways. Let's take a look at the structure of a pathway. A pathway consists of one or many variant streams. Each variant stream can only be in one and only one pathway. If not specified the pathway ID attribute, it implicitly belongs to the default dot pathway. Each variant stream may refer to 0 or 1 media group for each media type, out of audio, subtitle, and closed caption. Each media group may be referenced by multiple variant streams, even from different pathways. When we clone a new pathway out of existing one, we should not only clone its variant streams, but also the referenced media groups, if any. Then, to make it a new pathway, we need to modify the URIs of the variant and rendition streams of the newly cloned pathway. Let's take the 6 Mbps variant stream from the cloned pathway, for example. Let's say this particular variant stream has the URI as shown. To modify it to become the URI for the new pathway, the most flexible way is to replace the full URI line in whole. This means we need to store a full set of URIs in the steering manifest for each cloned pathway. However, in practice, we can usually do better than that. It is common in the industry to deploy streaming assets across multiple CDNs retaining the same URI path structure. And assets served from the same URI share the same URI host name and query parameters. If it's the case, we only need to store the replacement of host and query parameters in the manifest, and replace the components of all cloned URIs, and we got a new pathway. Let's take a look at how we can define the pathway clone in a manifest object. We added the pathway clones field with an array of pathway clone objects. Each pathway clone object defines a new pathway cloned from an existing pathway. In this example, we have one pathway clone object. The base ID field specified CDN1 to be the original pathway to clone from. The ID field specifies the new pathway ID to be CDN3. Next, we have the URI replacement field with an object of URI replacement rules. In this example, we are using the host and query parameter replacement rules, which should replace the host part and insert or replace query parameters of the streaming URIs respectively. In this case, we are replacing the host part to be cdn3.example.com and adding or setting query parameter foo with value xyz and query parameter bar with value 1, 2, 3. Let's try to apply the host and parameter URI replacement on our previous example URI. First, we have the resolved variant stream URI based on the multivariant playlist URI. In the steering manifest, we used host URI replacement rule. So for the host part of the URI, we replace it with cdn3.example.com and got the new host part for the new URI. Then we retain the URI path component from the cloned URI. Finally, we apply the URI query parameter replacement rule. Here we replace the full parameter because it exists on the original URI. Then we append the bar parameter because it's a new parameter. Then we have the replaced query parameter part of the new URI. The final result URI will be the URI for the 6 Mbps variant stream from the new pathway CDN3. We apply the same URI replacement rule to the rest of the variants and renditions in the clone pathway. For the 3 Mbps variant stream, we have the original URI and apply the host and parameter replacement rule to get the new URI. We do the same for the audio and subtitle renditions. After we apply the URI replacement rule to all cloned variants and renditions, we have a new pathway that serves from the new CDN host. Let's take another example, and let's say the streaming provider wants to serve their highest bandwidth video and audio streams from a specially tuned, fastest CDN host, different from the rest of the lower bitrate streams. This is where per stable ID URI replacement rule comes in handy. In HLS, stable variant ID and stable rendition ID attributes were introduced to identify variant and rendition streams. By setting them in the multivariant playlist, we can later reference each variant or rendition stream by their stable ID in the pathway clone object in the steering manifest, and assign per stream URI replacement rule. To define these particular special URI replacement rules, we need to assign stable IDs to all the variant and rendition streams in the multivariant playlist. For example, we assign stable rendition ID audio ENAC3 to the AC3 English audio, and stable variant ID video 4K DV to the 25 Mbps 4K variant stream. Then, in the steering manifest, we can add the two flexible replacement rules by referencing their stable IDs. For variant streams, we added per variant URIs field to the URI replacement object with a dictionary of stable variant ID to URI records. Here we specify to replace the URI of the variant stream with stable variant ID video 4K DV with the following URI. For the rendition stream, we added per rendition URIs field to the URI replacement object with a dictionary of stable rendition ID to URI records. Here we specify to replace the URI of rendition stream with stable rendition ID audio ENAC3 with the following URI. Here we see that after applying the URI replacement, all streams are serving from the new CDN3.example.com host, except the 4K video variant and AC3 English audio rendition, where they have special URI replacement rules, pointing them to the faster.example.com host and with different URI paths and query components. With pathway cloning, when the streaming provider dynamically spawns new CDN fleet, in this example CDN3, the steering server can add CDN3 as a pathway clone for existing clients in their steering manifest. It can also choose a region, for example Europe, to prioritize CDN3 as the primary pathway. When clients in Europe got the steering manifest update, they will steer the traffic towards CDN3. For the final part of this talk, let's switch our focus to the details of steering server to explain how to implement the server logic with concrete examples to steer client-player traffics for load balancing. One way to manage and orchestrate a swarm of client players and apply partitioned rules is to put every client into a bucket and apply the rules at the bucket level. It's simple to implement the bucketing at the steering server without maintaining any client session states. When the client player requests for the initial steering manifest, it makes an HTTP GET request at the steering server URI. The server then generates a uniform random number out of 12 possible buckets. When returning the steering manifest, the server adds the bucket number, in this case 7, to the reload URI attribute, which will be the steering manifest URI for the next request from the client player, so that the next time the client player requests for steering manifest, it will carry the bucket number in its request parameter, and the server can extract it and apply steering rules based on the bucket number. Now let's take a look at a simple bipartition steering rule. In this case, we want to steer 50% traffic to prefer CDN1 and the other 50% traffic to prefer CDN2. We can write such rule in terms of the bucket number. If the client player's bucket number falls in the first 6 buckets, we return steering manifest with pathway priority prefers CDN1, and otherwise return that with pathway priority prefers CDN2. Since clients are assigned to buckets uniformly, divide the 12 buckets into 6 buckets can bipartition the traffic evenly. Now, let's say a new pathway called CN3 is dynamically spawned. The steering server can advertise it using pathway cloning to clients doesn't know it from their multivariant playlist. One common question when constructing a steering manifest with pathway cloning is to determine the set of pathways that need to be included in the pathway clones array. The rule is to clone pathways that are not in the client's multivariant playlist. However, without maintaining any server-side states about the client session, how can the steering server know the set of pathways in the client's multivariant playlist? One way to do it is to include the set of pathways in the initial steering server URI as a query parameter during the generation of the multivariant playlist. In this case, the multivariant playlist contains 2 pathways, CDN1 and CDN2. Therefore, it includes them in the server URI attribute as a query parameter. Then, the client player will send requests to the URI, carrying the parameters to the steering server. Then, the steering server can extract the parameter as the set of pathways in the client's multivariant playlist. Then it can calculate the set of pathways to be cloned by subtracting the set of available pathways with the set of pathways in the client's multivariant playlist. In this case, the available pathways are CDN 1, 2, and 3, and the pathways in the client's multivariant playlist are CDN 1 and CDN 2. Therefore, the pathways that need to be included in the pathway clones array is CDN 3. Let's also take a look how the steering server can change its steering rules when there are 3 available pathways. In this case, the server wants to partition the client traffics evenly across CDN 1, 2, and 3. Rewrite this rule by returning pathway priority that prefers CDN 1 if the client's bucket number falls in the first third of the 12 buckets. Returning pathway priority that prefers CDN 2 if the client's bucket number falls in the second third range, and otherwise returning pathway priority that prefers CDN 3. This way, each pathway will serve a third of the client traffic. With everything we covered, you are now fully equipped to build your steering server with your own dynamic steering rules. Doing so can further improve the reliability of your streaming service. That's it for our updates in content steering this year. If you haven't done yet, try adopting content steering as your HLS CDN fallback mechanism, as it's more versatile and provides dynamic traffic steering. Please also take advantage of the new pathway cloning feature to improve your service reliability. As usual, check out the latest IETF HLS specification for more technical details. And remember to utilize our HTTP live streaming tools to validate your playlist as you make changes. Finally, if you have more questions or suggestions, feel free to reach out at HLSinterest@ietf.org. Thank you for joining and have a great day.